In this segment, we discuss what happens to a wave when it moves from one medium to another. In this particular case, if we look at the top figure, we have this blue wave here. We have a wave of a particular wavelength. You can notice the wavelength here that moves into this medium here. You notice here, as it moves into the medium, the wavelength changes. Actually, we have a smaller wavelength here. And then when it moves back into the original medium, we regain back the same wavelength. So actually, as the wave moves from this medium, medium 1, to medium 2, the wavelength changes from lambda 1 to lambda 2, where lambda 2 is smaller than lambda 1. And then when it moves back to medium 1, we regain back wavelength 1, lambda 1. Now, what else changes about the wave? If you remember, one key point to remember about waves is the frequency is determined only by the source, which means the frequency of the wave here, f1, is going to be the same as the frequency of the wave at medium 2. So frequency is not going to change. Now, what else can change? What's going to make the wavelength change? It is the speed. Now, remember what's the expression relating the speed of the wave, or the wavelength, and the frequency of the wave, which is lambda is equal to v over f. So for a constant f, if I have a smaller v, I'm going to have a smaller lambda. So in this particular case, what we are seeing, a wave gets slowed down when it gets into this bluish medium, and when it gets into medium 2. When it is slowed down, it has a shorter wavelength. But when it speeds back up, it gets a larger wavelength. Now, what we have here in red and pink is exactly the opposite. So here we have a particular wavelength, and you notice here the wavelength is much bigger. We cannot see it in this pink area here. We have half a wave here approximately. Now, so I have a larger wavelength here, meaning my speed here at medium 2 is larger than my speed at medium 1. And my wavelength at medium 2 is larger than my wavelength at medium 1. Remember again, the frequencies are the same. That's one important thing to remember when you talk about waves. Now, another thing to remember that's going to be useful to us, especially when talking about removing glare, anti-glare coatings, and then when we talk about the colors on the butterfly, like we mentioned before, what happens to the actual wave as it goes from one medium to another. Now, this particular case, we are showing just a pulse to help illustrate what happens. If I have a pulse like this one, moving from a medium where the wave moves with a speed v1 to a medium where it moves with a speed v2 with v2 less than v1, now we agreed now that the wavelength is going to be shorter inside medium 2, but what's going to happen to the pulse as it meets this interface? Two things are going to happen. Part of the pulse is going to be transmitted. Okay, the graphs here are not to scale, so this is supposed to be smaller than this, and this is smaller. Both of them are going to be are supposed to be quite smaller, but part of it is going to be transmitted, and we are representing it here. And part of it is going to be reflected. As what you notice here, I hope, the transmitted part is in the same orientation as the original pulse. However, the reflected pulse is flipped. So whenever I have a wave moving from one medium to a medium where it's going to be slowed down, the transmitted wave is going to keep the same phase or the same orientation. For the reflected wave, it's going to flip, meaning a 180 degrees change in phase. However, if we move from one medium to another medium where the velocity is larger than the velocity at medium 1, the transmitted one still keeps the same orientation, but the reflected one in this case keeps the same orientation as well. That's very important.